I'll go ahead and introduce our presenters here today, and I'll hand it off to them to get started. So welcome again to the TRX webinar here for the month of May, where we have CEAD Group presenting. CEAD recently joined the America Makes membership in the last year, and Roger and Hugo are going to give a presentation today on their technologies. And with that, I'm going to pass it over to, I believe, Hugo to go ahead and get things started. Hugo, take it away.
Good afternoon, good morning, everybody. Thanks again for the introduction. Just to quickly introduce the two speakers today. So I will start. My name is Hugo, and then Roger will also present today. Just to start with, just raise your hand. Are you the people that are aware of CEAD or large format AEM? We'll try to be as less boring as possible, and just to go through the history of CEAD, the technology, and what is LFAM. But it would be interesting to know if you're already aware of LFAM or not, to know where to spend more time during the presentation. So feel free to raise your hand if you already know CEAD and if you already know the large format additive manufacturing. So few people already aware of it. So that's perfect. So first of all, I would like to start with just explain a bit who we are at CEAD, when we started, where we started, and where we are right now. So if we do a step back before CEAD, Lucas and Martin, which are, I don't know if you can see my mouse, but which are the two guys in the white shirts, founded a company called Leapfrog. That was a B2C 3D printing company based in the Netherlands. At that time, they were competing against Ultimaker, for instance. So they just worked on that for a couple of years. And in 2014, they just sold Leapfrog because they wanted to go more to B2B and industrial equipment. So at that time, they started CEAD, which, by the way, means connecting engineering and design. So for the first year, they just moved towards special machines, developing a new machine that didn't exist for specific needs. And in 2017, they just wanted to go back to printing, but stay within the industrial environment. So the idea was to mix both, and that's where the CFAM Prime started. So the CFAM Prime is an old machine that's a gantry-based large format system, which doesn't exist anymore, because in 2019, it has been replaced with the AM FlexBots that you can see right here on the image. So the FlexBot is a robotic turnkey solution that runs out of a Como robots and a Siemens CNC controller. And then since 2019, we rapidly grow to more than 50 employees, installed in 2023, the largest robotic system for printing worldwide, which is 120 foot long. And then we continued in 2023 with establishing our Inc. in Detroit, so with CEAD Group Inc., with the first North American employees in sales, support, and services, and continue to grow with more people in the US, more installations, with in 2024 more than 250 systems, with around 70 just in the US. And we also installed in 2024 the microfactory at Additive that most of you probably know because it's quite famous on the social medias. And in 2025, we also launched the Fiber Levelis, which is a system dedicated to print boats, which I guess most of you already seen the time lapse on Instagram, LinkedIn, TikTok, you name it. So that's a bit who we are, where we come from, and to give you a bit of an idea on where we go, specifically for the US. There's a lot of attraction around maritime tooling and all these things. So we are expanding our US operations with more local support, more spare parts, more infrastructures to be able to support our customers domestically. And I will give the mic to my colleague, Roger.
Yeah, hello everyone. Nice that you're here. I'm here to discuss a bit what LFAM actually is, because there are many kinds of additive manufacturing. This is a group for additive manufacturing. CEAD, yeah, we are in the category of fused deposition modeling, and then to be precise, the fused granulate fabrication, which means that, and FFF, a lot of people maybe know that because that's the small printer, right, on filament. Basically, it works the same in principle as the filament fabrication, in the sense that the plastic gets fed into the nozzle, heated up, molten, and then you build up the shape with that molten plastic, right? Often these are not filled, the filaments, but they can also be filled. But FGF works with granulate, so this is the pelletized form of the plastic, which often is the state of the plastic before it is a filament. It is just like an injection molding system working with a large screw inside a barrel that feeds the material forward to the nozzle, heats up the pellets gradually, and deposits layer by layer to build up the shape you need. And as you scale things up, things become also enlarged, like the temperature of the layers. You need to work with the precise temperature of the layer, or you will have a melting or a collapsing shape. Or if it's not hot enough, then you will have delamination between the layers.
So now it's time to ask you some questions. So we'll go through a quick quiz about large format AM, and the idea is to show the difference between what people are used to in desktop printing and in large format. So the first question is, we just want to print a box, something very, very easy, like 3 feet by 1 feet by 1 feet. So that takes for like 60 seconds per layer, and there's around like 100 layers. The question is, which extruder to use to print the box in a minimum of time. So we have a lot of different extruders from 25 pounds an hour to 185 pounds an hour. And the question is like, which one to use to ensure that we can print that box the most efficiently. Saying if you could send the first poll. Oh, yes. So you have different answers. The answer A is an extruder that can do 25 pounds an hour, or can be 55, can be 130, can be 155. Just wait a few seconds for people to reply to the poll. I unfortunately cannot see the percentages of reply. But I see someone that replied D, which is obviously the trap. So if I just explain you a bit why it's not a big extruder, that means that you can print faster. You have for sure more throughputs, but there are a lot of things about the material itself in large formats. So when we have a look to the desktop printers with filaments, the more materials we can extrude, the better it is, because the material cools down so quick that we don't have to take care about the thermal properties. But in large formats, if you're too hot and you bring too much material, that will just collapse, because the material will be liquid and you will not be able to build the layers on top of each other. So there's something called the layer time that is based on the material property, on the layer width and layers like bit size typically, and the environment, if it's cold, if it's hot, and so on. That's fixed a certain time per layer. You can do whatever you want, you will not be able to be faster than that. So in that case, if it's 60 seconds per layer, that means that we can roughly print it in 1.5 hours, and it weighs 40 pounds. That means that we have on average 25 pounds an hour of output. So having a huge extruder will just use it at its minimum capacity, and it's kind of useless. So in that case, around 25 pounds an hour, the answer could be answer A with the E25, which could be the maximum output of the extruder, or could be the answer B with the S25 with 50 pounds an hour, which will be at 50% of its capacity. So something very important with large format is not big extruder doesn't mean more production, and a slow and small extruder will sometimes be limiting if you need more output. So that box was quite small, but if we print a very large one, then we'll need a bigger extruder. If we go to question 2, here is the chimney cap, very basic a product that we find on all the roofs. That is the kind of part that requires a lot of different process with cutting, bending, welding, bolting, and there's around like 12 parts in these products. And the question is like, can we print it, and does it make sense to print it? Because sometimes it's like technically feasible, but commercially it doesn't make sense. Like if it's longer, if it's more expensive, then it's kind of useless. So let's go for the second poll. Then could you up? Yeah. So answer A, yes, we can print it and it makes sense. Answer B, well, see here, it doesn't make sense. So just give a bit of time.
It looks like we've got a pretty even split on this one, 50-50.
50-50?
50-50. Oh, let's see who's right.
So the answer is yes. And there is a little reason for that. If we take the standard cap, in terms of weight, around like 16 pounds. If we print it, depending on the materials, if we use low density and different materials, we can go up to 10 pounds. So we can save on material cost thanks to that, depending on the cost per pound. But the most interesting part is about the production time. If you want to produce a chimney cap with the regular methods, you will need around 12 parts and a lot of manual labor to be able to assemble everything, and a lot of different skills, because that's not the same skill to laser cut, water cuts, the sheets, to bend it, to weld it. So a lot of different people to be able to do it, and it will take like roughly 1.5 days to do it. If you print it in 5 hours, you can just print it in one piece. So you save a lot in terms of time, weight, and then in terms of cost. And if you want to even increase the production, instead of printing one at a time, you can print multiple of them at a time. As I mentioned earlier, the layer time is fixed. So in the same amount of time, instead of printing one part, we can print 2 or 3. So there's a lot of end parts like this one that sounds basic parts, but because of all the labor that is required to be able to manufacture them, it makes sense to print them. Next question. If we go back to the first box that we had on the question 1, now I want to produce 100 of these boxes, because one box is kind of useless. I need 100 of these boxes, and I need to do them in 1 week. The question is, will I use the same system as the first question with a small extruder, or do I use a bigger machine? And if you can send the poll, please.
Right, we've got results trailing in, and it is leaning heavily on answer B. We're about 2/3 to 1/3.
Nice.
2/3.
So that's the exact answer. So basically, a small system will allow you to print the box, but you will print the box in roughly an hour and a half, but you will have to print them one by one. If you have a bigger machine and you scale and wants to print more parts at the same time, then we can go with a bigger extruder. So we've seen that with one box, we have an output of roughly 25 pounds an hour. So that means that if we have an E40 extruder that can go up to 130 pounds an hour, we can print up to 5 boxes at the same time. With travel moves, all this stuff, it will take just a bit more time than printing one. But basically, if we print 5 boxes every 2 hours, we can do roughly 4 batches a day, which allows us to do 100 parts in 1 week. So large format AM can be used for prototype one-off parts, but it can also be used for serial products. Of course, there's a limitation. If you want to do thousands of parts, like tens of thousands, then auto process will be better. But for small batches and small projects that doesn't require any tooling, any preparation, then it's way better. If you want to do 100 parts and you want to get them injected, if you have to pay for the tool for the injection, you'll wait a couple of months. It will cost a lot before you can even start producing. So that's one of the advantage of the large format AM. You can produce small series quickly, and if you need, you can also change the design. Now, last but not least, everybody loves to print a Benchy once we receive our desktop machine. And the question is, can we print it with large formats?
All right, we've got quite a few responses coming in. It is teetering. They're still coming in. We're just a bit skewed past 60-40 with A coming out in front. Yes, we can print it.
That's a bit of a tricky question. It's like at the same time, yes and no. So I will just like start a video for you to see how to slice it. So if we want to print that with a desktop printer, we will just print it bottom up, put some infills, and if we need some support at some places, we'll just do it. But as we mentioned earlier, to print in large format AM, we only print the contour. So there's no infill. And if you're above 45 degree in terms of overhangs, that means that you cannot print it. So you can see in some areas we have some challenges with overhangs, and we'll be able to see that on this simulation. So we'll print at 45 degree, and you can see, well, there's internal things, but you can see that some places start in the middle of nowhere. So these places will need some support or some redesign to be able to, yeah, that one is very good to see it. The pockets that you have here on the middle needs some support because it starts in the middle of nowhere. With a desktop printer, we'll just like print infill and start printing on top of the infill. In this case, we'll need to redesign the Benchy to be able to print it. So a big Benchy is printable, but we'll have to review the design and change some part of it. So yeah, that's pretty much it for the quiz. I hope that's allowed you to better understand what is achievable, what is not, and what are the differentiation between desktop printing and large formats. And now we'll just dive a bit into the large formats type of solutions.
Yeah. So our presentation, of course, is about microfactories. And that microfactory is a solution that has been shaped by the industries that we work with. So for the US, the situation for the US is that basically there's a large reshoring move. 36% of US manufacturers, they're, instead of doing offshore production, they want to do production in the US again. And that doesn't change the competitiveness that there already is, right? So people are used to quick iteration, low prices, just ordering overseas and getting the tools for a low price. And in parallel, they can do their processes in-house. And there's a move from serial production and customized local solutions. But in many industries, the workforce is the bottleneck, right? So the shortage of skilled labor in the traditional processes, like skilled woodworkers or mold makers, since everything has been done overseas all the time. Because traditional manufacturing is still being used mostly. Let me mention some points there. multiple production steps, like you saw with the chimney, assembly, bending, multiple toolings needed to make the different components, multiple kinds of machines, milling machine first, and then you need something that presses, for example. There is as I said before, manual labor needed for the process. And often with traditional manufacturing, you're thinking of maybe an extra building for your inventory, because you need to have parts or tools on stock. You have a lot of waste. You're, for example, making a pattern and then you mill a block of polystyrene. How much material goes away? With large format additive manufacturing, that's a bit different. So those points that I mentioned, let's name these 4: long lead times, high costs, sustainability, and lack of skilled labor that we see being the biggest problem. By designing, for example, the benchy that you saw before in CAD, so that it can be 3D printing, which is called design for additive manufacturing. I think you all know this here, since you're working with different kinds of additive manufacturing. You can add complexity to the design as long as it's designed right. Like the chimney that you saw before, you can in one print integrate, for example, the edge inside to drain the water. It's the same layer. It's the same layer. So if you design it right, your production with LFVM, you will just have with the slicing, you have a net shape which it will print, so you use less material. With 3D printing means you need less components, so you can get it more local sourced. And 3D printing also offers recycled materials as material, and there's less skilled manual labor needed. So in the end, that process makes it that there are reduced lead times for example, tool making, lower cost involved because of the lead time, because of the material cost, just because of the fact that you can, with that shorter lead time, produce more, as well as decreased footprint, because basically all those steps needed require machines. Now it's in a single machine, and that is a key part of automation. So the challenge there with additive manufacturing, with existing systems, is basically making that move from a single system to really a part on the production floor. Additive manufacturing, large format additive manufacturing is proven, and we have a lot of customers. Right now we have 270, a bit more, I think, in aerospace, automotive, marine, construction, but also other segments, as we'll be showing later. But if you look at a single system, often they produce a part on the work floor and then they stand still and they're waiting for the next part to be done. But if you want to move from a single system to something that is part of an integrated larger picture, you need a different kind of additive manufacturing system. But every industry requires a different kind of solution. For that, we designed earlier, that was one of our starting systems, the FlexBot, which works on a CNC control, Cematics, which is an industry standard, but is also scalable. So it can be configured to different sizes. So you basically you can start with a basic system and upgrade that as you become more confident. You can have a hybrid process, so not only 3D printing, but also milling, as you can see here on the picture. In the back here is a milling spindle. And if you use the right software and the material, you can decide what the right software material is for your application, and the right hardware that is scalable. You can be very successful with a system like this. And that is thanks to all the knowledge that we have through our partners and the collaborations that we've had. That is the robotic system, but we also had basically last year, or 24, we released the Flex Cube, which is a gantry system, and that is also CNC controlled. So people that are already working with CNC control systems, for them it's the same kind of interface. So very low barrier learning curve. This system is also very compact compared to a robotic system. So this is around 8 feet high, and this system is 3+1 axis, so that can print horizontal or 45 degrees, as you saw with that benchy model that was being tried to be printed. Basically this system is also hybrid, so it does printing and milling. So again, makes the space in which you produce very compact. And yeah, key in these kind of systems is that scalability. So both in sense of the size of the printing area as well as the extruder. Maybe first you, as in the examples from Hugo, you want to print a single box to see how to print that single box. But after that, you want to move towards printing 100 boxes. And then the system, the right system will allow you to upgrade to a different extruder without having to completely reinvent the system. That is for the extruders, that is for the size of the print bed, for the linear track, but also features like, for example, heated print beds, which make sure that the layer doesn't cool down too quickly. You can have, for example, data logging or scanning tools on that system, so that you have a fully hybrid system and you can customize it for your application.
So as you can see, there's a lot of different configuration based on the need and based on the application. And you might like ask yourself, okay, which industry are targeted? And the answer is like a bit of everything. We have customers doing aerospace tooling with autoclave tools, trimming jigs, infusions, also customers doing architectures, printing furniture for Disney, printing bars and things like that. Or like also you might have seen some boats that are printed. But we also have very particular system, for instance, printing windows. So there's a lot of different application depending on the needs, and then each application will require a different type of system. I just would like to dive into two applications today, two examples that are like very important in the US, and the first one will be the maritime. So you've seen the current administration that has committed to like 2.1 billion to the USV markets, and it's like still growing every day with the idea to be
Is it okay? Yeah, I see Roger moving. Roger, you want to go ahead and take over? I think Hugo got disconnected.
Yeah. Let me get back to the slides.
Apologies, folks. We'll get started back up here in just a moment.
Let's see. This is
Perfect. All right, Roger. Thank you.
yeah. Let me get to the right slide here. A grid view.
All right, and while Roger's skipping through there, if anybody has any questions or anything, feel free to type them in the chat as we go. There's also the Q&A section for some of you that have that feature enabled. And yeah, we'll continue on here shortly.
Yeah. So running on.
Sorry,
I back.
think I'm back. Sorry, it sounds like my internet connection disappeared. Can you hear me well?
Yeah, I can hear you loud and clear, and you can take over the presentation. I've loaded the right slide, so feel free to go ahead.
Yeah, thank you, and sorry everybody for that. So yeah, I was just saying that there's the ambition to produce a lot, produce more, but right now the money is not the problem. The problem to manufacture locally and domestically will be the manufacturing speed and the people to.
I think we lost Hugo again. Oh, there you are.
Am I back? Yeah, I'm sorry, that's weird. Sounds like the office. Yeah, sorry, I was just saying that there's an ambition to to manufacture a lot domestically, but we don't have the manufacturing speed and the people to do it. So if you want to do it traditionally, you'll have to go through tooling process, and because of the quick iteration of the USD markets, it's impossible to use the tooling, because if we start doing the tooling and wait for the tooling to come in 6 months, then we'll iterate to the next version in the meantime. So the only solution is to use something that can be
The internet is having a bad day today.
If
Roger,
do you mind there we go.
taking it, because it sounds like I have a lot of issues. Yeah, Roger, do you mind taking it, because it sounds like I have a lot of issues with the Wi-Fi in the office.
Yeah, of course. So with that investment of 2.1 billion and the development of the technology of unmanned technology, the designs are moving faster than the tooling, right? The time that you have to wait to get a tool done, there's already a new design, and that is making it very hard to keep up with the developments in the technology. So basically, their manual labor becomes the constraint, because you cannot make the tools in the volumes and in the time that are required. So with LFVM, you remove that bottleneck, basically printing the hole directly. And the examples you see here are ranging in meters. I know it from 8 meters on the left to 2.5 meters to a 2-meter design. And yeah, basically, if you have a system that, like this box, can print multiple of these, you can print the hulls of these USVs without being dependent on the workforce that you would normally need to make the glass fiber hulls, for example. And so here, going into that example that you saw on the right, during BOMA, this is Bold Makina NATO exercise that was held in the Netherlands. We were asked to demonstrate a small 8 feet USV as well as a 40 feet rib design boat. But looking at that USV, which we're discussing now, the system, the Flex Cube system, was used here, by the way. There was a very rapid deployment. In 2 days, the system was set up and ready to produce. The system was in a forward base position on the floor that normally for larger systems would not be enough, but for this system it was. People could sit next to the system, iterate on designs, and the printing took 10 hours. Basically, you could redesign, print, and develop very quickly instead of waiting for the different steps in traditional production. The weight of that hull was 65 pounds, to give you an idea of that, of the USV. And yeah, they were very impressed with the reduction in lead time, the setup, also meaning that you can deploy the system in a few days, wherever it is needed, close to where it's needed, and the lead time linked with that is just such a big improvement. Then the other main issue is the tooling industry, right? So as I said before, companies are used to order a tool offshore in Asia or in India, and getting that to the US. So they're dependent on the supply chain, as well as the traditional process takes long. You don't have that within a few days, that tool. And the situation is that with the current line in how much production will come back to the US, 2.1 million jobs will not be filled because there's such a lack in labor force. And try to educate these people, it's going to take multiple years to get them back to training, and then they also need the experience. So this is really a big problem. And 3D printing removes that hurdle, right? Because newer educations are more digital focused, 3D design, and that way you can have your skilled labor focusing on those few steps in the production line, and have enough people that are trained with the digital means to running the production. This mold that you see here, it's an 2 meter by 2 meter by 800 millimeters tool, so quite large. That is used for the, if you can see my mouse, for this part, which covers the hydrogen fuel tank of this racing car. It's a carbon fiber component, and it took only 36 hours to print it and 40 hours to mill. So basically, within a week, you can have a tool ready for use instead of waiting multiple weeks or even months for the tool to be there. And this lead time reduction, I think, is clear, but the cost is also significantly lower, around 40% lower in this case for this project. And besides that, you're also not dependent on supply chain on transport by sea. It's just all closer to home, so you're capable to do much more in a shorter time. These are just singular examples, but that going back to that micro factory subject, in essence, scaling those two examples so that USV production and tooling production can be done on a larger scale. So basically having what we call a micro factory, you can have multiple machines running next to each other. You can print on demand because you can have multiple machines working on a project. So looking at those lead times that you saw before, you can have, with what you see here, these are 6 FlexBot systems with E40. You can print multiple parts at the same time, and you can have multiple robots printing at the same time. And you don't have to store all the components in a warehouse because you have the digital files, which take no space, right? Only gigs on your computer. And you have a storage of material, which is very efficient. It's pelletized material. Instead of those parts that many are used to needing to store. Often it's like a whole separate building, which is as large as the facility, with molds that they have to keep for 5 years, 4 years as a backup. And the right way to do that is often starting small, right? So as before, you print with that single box, you decide what kinds of application are a good fit, which need redesign, what is the best workflow to produce them, and then scale that to a real production line or part of an existing production line, like tooling. So in essence, the message here is a robotic microfactory or a microfactory, because there are also gantry systems that are a key part in this in coming projects, is not a room full of machines that just do their own thing and work and then have to wait for the next step, but you can have them as a full production architecture. You can see it as a modular network of cells that can operate in parallel and that you can scale as you change, for example, the volumes or the size of the components that you're making. And in essence, that system, if you have the right system, it's always reconfigurable and flexible. You can, like Hedy, they do a very large range, a larger range than that they did before. And that helped them to grow because the system is also designed to grow. So that concludes our presentation. Before we go to the questions, I would like to thank America Makes for giving us this opportunity and for the great collaboration leading up to this webinar. Really appreciate it. Yeah, I'm very curious to hear something from you as well, right? Are you looking at large format? Are you maybe seeing some hurdles, or you have some doubts? Are you running into problems?
Perfect. Thank you, Roger. Yeah. You should be able to hop off mute if you'd like to have direct dialogue, or if you have anything that you'd like to share, go ahead and feel free to use the chat. We'll go ahead and kind of jump off with Roger's initial question there, and then see what the attendees are interested in hearing about. So if you have anything that you'd like to share or ask, go ahead, come off mute, submit them in the chat or Q&A, and we'll get answering.
Thank you, Peter.
All right. Looks
Yeah,
like
so
we
I
have
see a question from Clark.
Clark Patterson. Perfect. Go
Yeah,
ahead,
I
Roger.
think this is a good one for you, Hugo, since you've been working with the system firsthand.
Yeah. So the system itself doesn't have any thermal monitoring camera, but it's possible to plug it through the data logging platform. So the data logging platform is a platform that's just monitor all the parameters of the machine, and it's also possible to plug cameras to this platform. So natively not, but with this option, it's then possible to plug a thermal camera. And then it's just a matter of like creating the loop to be able to have a retroactive loop to actively change the temperature.
Yeah. And so that's because of this Siemens system, right? We can extract data from all the different components. The full system works via Siemens Numeric, and that allows us to log all the data with the same time slot for every measurement that's done on the system. And that system is also open for you to add things like infrared camera, which, because of that data logging principle, can be used to improve your process or to log your process and visualize it as well.
Perfect. And I'm actually going to read these out. Hopefully the recording can grab them as well. But I'm going to skip Jack's question for the current moment, as Peter had a follow-up on Clark's. But Peter Dom asked, along the lines of the question from Clark, what process control / data collection information part of your systems?
Let me read that, Peter. Along the lines of the question, what process control data collection information part of your system? So let me think about that. Process control. Basically, the data extracted is turned into a database that can be loaded into most SQL kinds of systems. But you also have a live feedback, which is connected to a system, a software that you can use to, for example, set alarms with certain values. You can set certain points in the print that you would like to extract the data from. Plus, you can then, with a data logging system, store that as well there. You can use that data, for example, for certification for certain kinds of components that are in need of a full control and monitoring of the process. Does that answer your question, Peter?
I'll come off mute. Hi, thank you, Roger. It was, yes, I just put another one on there. It's just asking what parameters, what things are you tracking, controlling, monitoring yourselves right now? I'm sure there's a lot that can be done, but what are you guys using? You know, which KPVs are you, key process variables are you looking at to keep the process in control?
Yeah, thank you for your question.
So there's more than
that's
parameters.
Yeah. Go ahead, Hugo.
So the data logging platform monitors more than 300 parameters. That's everything about the system. So that will be the position, X, Y, Z, rotation, position of the track, the pressure in the barrel, the set points for the different hit points. That would be the acceleration, the speed, everything in the system. Every sensor is monitored. So you have all this information in the time, and for every second, you know what is the status of each sensor. So that's the sensors, that's the drive, that's everything.
Thank you. So much so it's hard to discuss here. I understand. Thank you.
Perfect. Thank you, Peter.
We can have follow-up contact with you, Peter, if you want to know more. Then we can share, of course.
Yeah, Roger, did I see either the first slide or one of the last slides had your guys' contact information on them?
Yeah,
on
that's
the
correct.
first slide.
I'll move to this
there you go.
one. Feel free. Yeah, feel free to reach out to us, to either of us or both. Go ahead, Zane.
Yeah, no, I was just going to say the exact same thing. So feel free to reach out to Hugo and Roger on the CEAD group team. Their contacts are here. And then I'll jump into the next question since we skipped over Jack's. Jack Kennedy said, is there any theoretical limit on the size of a maritime vessel that your system can produce? And how many different polymer feedstocks do you currently support?
Yeah, so basically, theoretically, with the right output, you can have as long as a layer as that you can make. Like, for example, the E50 is used right now to print houses of 4 meters by 4 meters. Am I saying that correctly, Hugo?
Yeah.
Then
the thing in terms of length, it's possible to print as long as you want. It's just a matter of like length of the track. The thing that will be a bit limiting will be the size of the beam. So because you need to have a certain layer time, and the machine has a maximum speed, you can print up to a section of around 4 meters wide. So that would be around 13 feet wide by 6.5 feet tall. So as long as the section fit into that, then it's possible theoretically to do up to whatever you want in length. But we see that the good ratio is up to 40 feet. So usually what we do for the fiber navalis, which is the machine dedicated for printing boats, you can print boats up to 4 feet long, 40 feet, sorry. And to answer the question in terms of feedstock, the machine is open source. So as long as you use thermoplastic filled with like fibers and stuff like that, or also virgin plastics, then you can extrude them. I cannot guarantee the results. I would recommend to use thermoplastics developed for large format AM, but theoretically you can extrude whatever you want. So as long as it's a thermoplastic in pellet stock.
Yeah, and also a good point here, I think, to mention is that large format, since you enlarge all things like temperature management, but also like warping, that composite polymers work best for large format 3D printing. That is short fiber reinforced thermoplastic polymers in pellet form. We currently have 300 materials fully tested and custom setting parameters for the heating zones, as well as ideal layer times based on the dimensions of the beads. So in essence, theoretically, we can support any polymer, and yeah, if we can research the right settings for a polymer, then we can print it.
Thank you, Roger. Thank you, Hugo. We've got about 5 minutes left, so anyone else that has questions, feel free to throw them in the chat or pop off mute. I've had a couple good ones here, and then I noticed that you had a couple more slides there. I don't know if there were more examples or anything like that that you wanted to jump through, Roger, but feel free to run through those as well.
Yeah, so the slide I got since we were discussing maritime systems was this one, which shows robotic systems that we have out in the field. So these are real systems that are used in production. On the top left, this is the longest flexbolt system, which is 120 feet. It doesn't print 120 feet long boats because basically connected to what Hugo said earlier, there are some regulations, and there are also with that output a limited size to what you can print. But they printed up to 40, just a bit below 40 feet hulls. That is really for production. This is used in UAE. In the middle here, we have a system that's placed in Europe, which is more for R&D work for maritime. So you can see 2 robotic systems with E40 extruders, as well as a custom print bed here, which is not horizontally placed, but vertically placed. On the top right, you see the machines and the parkings for the extruders for the hybrid systems we have at Heady. So these are all standing in line, ready to be to pick up either the milling head or the printing head. Then that is, of course, for really high volume manufacturing of all kinds of furniture, interior design. They do a lot of interesting parts. Maybe you've seen some of their parts used in attraction parks or in movies. But there's also a right system if you are working more with bespoke systems. So here you see a 4x2 flexbolt system with a heated print bed. And Valas was already discussed. But on the bottom right, you see a kind of a different print bed. You don't see it fully here, but it's a rotary print bed of 4 meters by 4 meters, with which, of course, you can then print very large shapes. This is used for foundries for really large patterns for sand casting and for concrete casting molds, which also often are much larger than the standard molds.
Thank you, Roger. All right, Clark has another question. Has the continuous fiber been canceled completely?
Are you going to take this, Hugo, or
I
shall I go ahead?
Yeah, I guess on this one, Clark, you mentioned about the ADLAM. So the ADLAM toolhead is a mix of continuous fiber and short fiber. That's the idea is to print a sandwich of continuous pre-preg and short fibers feedstock. There's some systems that are using this toolhead. In the US, there's the University of Maine that use it. At the moment, it's mostly used in research and development, since it's not fully ready for the industry. So it's still used and in development as new versions comes every couple of years.
Thank you. All right. So I believe we are up on time. So if anybody would like to follow up with Roger and Hugo, feel free to reach out to them directly. Their contact information is there in the chat. This chat should be available to you following the call as well. With that, I'd like to say thank you, Roger. Thank you, Hugo, for your presentation. And thank you all of those that attended. And feel free to reach out with any questions, and look forward to seeing you guys in the next TRX webinar. Thank you.
Thank you, Zane. Thanks, everyone. Have a great day.
Everyone.